So let us now explicitly evaluate the dominant contributions. And obviously, as this integral is real, why do we see it? Because only because of this square root, only even part survives, and even part of this exponential is just cosine, which is real. So we need to evaluate. With that in mind, we understand that actually only one contribution is enough, and then we take a real part. So simplified version of this I of lambda is two real parts of integral over C1. C1 is this part of contour of exponent of I. And now, in writing this, we neglected this part I2, which is exponentially small. So in order to evaluate this, we need, of course, to parameterize this part of contour. But our general understanding, and we will see exactly how it works in this example now, our general understanding is such that only tiny contribution of this contour will contribute, and the width of this part which contributes is controlled by lambda. And this contributing part becomes smaller and smaller as lambda becomes larger and larger. And so, as a result, we can actually not care about exact shape of this curve, but only about its shape in the vicinity of the endpoint of the integration domain. And we actually can write z equal -1 plus it. And now integrate over t from -infinity to infinity. So finally, the expression for the dominant asymptotic contribution becomes two real parts of integral I dt. So this I comes from the change of the integration measure. Here we go with exponent. We'll write it down in a second. In addition, there is a square root in the denominator. Let us start from the explicit evaluation of what stays in the exponent. So we need to take our z cube plus 3z, substitute z equal to -1 plus it. And so it becomes at -1, it is -1 and -3, so this is -4. And then something which is proportional to it. And what else is here is just derivative at -1. That is 3z squared plus 3 at z equal to -1. So this is nothing but 6. So this is what goes here, -4 plus 6 it lambda. And now the square root in the denominator. This is 1 minus z squared. So this is just 1 minus z times 1 plus z. And this becomes, so 1 plus z is just it. And 1 minus z can be simply replaced with 2, because z is approximately -1. So here goes to it. And integration goes now from 0 to infinity, which corresponds to this part of the contour. So now we can perform an explicit evaluation, and of course there are some factors which simply factorize, such as square root of 2, which comes from this to these factors. And then there is real part, and this real part is here we have square root of I, which comes from partial cancellation here, and exponent of -4i lambda. And the remnants here come from evaluation of the following integral. here comes 6 to 60 lambda. And of course, here is one of the most important points. And in fact, the integral takes such a form that we immediately see that, in fact, indeed, only region of the size of the order of 1 over lambda, which is small, of course, contributes to this integral. So, and finally, this becomes up to some factor which can be evaluated using the gamma function. This becomes, after change of the variable, 1 over square root of lambda. And this factor is purely real. So, substituting all this here, we can now write down the final result. So here it is convenient for the square root of phi to use exponential representation, and the result becomes. So this is our final result. And of course, this is just nothing but cosine with some phase shift, and explicit evaluation of this factor, which is just number, will be one of your exercises to this lecture. But let us summarize a bit what we have just learned. And we learned some very general methodology for evaluation of complicated integrals over the finite domains. And the crucial steps are the following. First, identify lines along which the integral almost doesn't oscillate. They are given by constant lines of the imaginary part of the exponential. Then guess, using the convergence analysis, how to decompose your original contour into the set of constant phase contours. And finally, estimate contribution of each of them separately. So here is an example of this program performed for the simple integral. You will, of course, have more in your homework exercises, but in order to please take care to perform these exercises with all details, because they contain all the wisdom of the stationary point technique, and you will find them very illuminating.